Students, today we are going to study alternating current AC through a resistor. For this, let us consider a pure ohmic resistor of resistance R, and R is connected to a source of an alternating current. If we say pure resistor, pure ohmic resistor means pure inductance. Okay, here you see in the circuit diagram R, a resistor of value R, resistance R is connected with alternating EMF. Okay, so that I current flows throughout the circuit. Very simple diagram. Resistance R, resistor R of resistance is connected with alternating EMF source, so that current I is flowing throughout the circuit. Let us consider E be the instantaneous EMF. From peak value of instantaneous EMF, we know E is equal to E naught sine omega t. Now, the instantaneous EMF due to the source is equal to instantaneous value of potential drop across the resistor R. If I is current flowing throughout the circuit, then according to Ohm's law, we can write E is equal to IR, or I will be equal to E upon R. Now we substitute the value of E from equation 1. Then we get I is equal to I naught sine omega t upon R. Let this quantity E naught upon R be I naught. We know that I naught is the peak value of alternating current. So we can write, that is, I is equal to I naught sine omega t. Let it be equation number 2. Now, from equation 1, that is E is equal to E naught sine omega t, and from equation 2, I is equal to I naught sine omega t, it follows that alternating current is in phase with alternating EMF. When AC, alternating current, flows throughout the circuit, okay, alternating EMF and alternating current, we are getting both are in same phase. So graphical representation, you see, if we take EMF E or I on this axis, y axis, and omega t with x axis, then we get, see, I have drawn dotted line for current and solid line for EMF. This EMF and current both are in phase. So come to phasor diagram for alternating EMF and current. We get, for this phasor diagram, we get one straight line, okay, and the straight line is having constant slope, that is the straight line which represents alternating current as well as alternating EMF. Since both are in phase, so both are represented by this straight line only, and the line, the graph, makes an angle of omega t, with OX axis. AC through an inductor. Let us consider a pure inductor of inductance L having no ohmic resistance. If we say pure inductor means will have no ohmic resistance, and the inductor is connected with alternating EMF supply. So that here you see our circuit diagram. This is having inductance L. So L, power supply, okay, alternating EMF, and when we complete the circuit, current I flows throughout the circuit. Now we know that instantaneous EMF is E is equal to E naught sine omega t. Put it equation number 1. See, I current flows throughout the circuit. Okay, so we can say di upon dt, that is rate of flow of current in that instant. So we can write the instantaneous induced EMF produced across the coil, produced across the inductor. We can say this instantaneous induced EMF is equal to minus L di upon dt, where di upon dt is rate of flow of current in that instant, in that interval of time, in for that particular time. Now, therefore, total instantaneous current of the circuit will be this E plus minus of L di upon dt. Here it is written total EMF E is equal to minus of L di dt. Okay. Now, since there is no circuit element across which potential drop may occur, so therefore E minus L di dt is equal to 0, or we can write E is equal to L di upon dt, or di is equal to E upon L dt. Okay. Now, the instantaneous EMF due to the source is equal to instantaneous value of potential drop across the circuit element. So, we can derive the relation. And one more thing, there is no circuit element across which potential drop may occur. Okay, that's why we are having di is equal to E upon L dt. Now, substituting the value of E, that is E naught sine omega t, we get di is equal to E naught sine omega t dt upon L. Or for total current, we can integrate the equation. After integration, we get I, total current, is equal to E naught upon L integration of sine omega t dt. After integration, we get I is equal to E naught upon L into minus of cos omega t upon omega. Okay. Now, using trigonometrical relations formula, we can write I is equal to E naught omega L sine of omega t minus pi by 2. Here this omega L, you see the omega L, this value omega L has got the unit of resistance using Ohm's law. V is equal to IR or E is equal to IR. or E will be V or E upon R. So comparing with that relation, we get omega L. Omega L is nothing but acting as a resistance. Therefore, this omega L is called reactance of inductor, reactance of inductor or inductive reactance. Okay. Now, I is equal to, we can write for omega L, we can use this xi L. Okay. Substituting here, we can write I is equal to E naught xi L sine omega t minus pi by 2. Okay. And if you see the relation, and if we substitute I naught for this complete E naught upon x xi L, we can write I is equal to I naught sine omega t minus pi by 2. Here you see E naught over psi L is equal to I naught. Substituting in the equation, we get I is equal to I naught sine omega t minus pi by 2. Okay, let it be equation number 2. So, first equation was E is equal to E naught sine omega t, and our second equation is this one, I is equal to I naught sine omega t minus phi by 2. From these two equations, it follows that the AC lags behind the EMF by a phase angle pi by 2. Here you see we are having sine omega t, and here sine omega t minus pi by 2. So we can say AC alternating current lags behind the EMF by a phase angle of pi by 2, or in other words we can say EMF leads the current, EMF leads the current by a phase angle pi by 2. Now, graphical representation of this AC through an inductor. Now we consider EMF E or I in this, on this axis, and omega t as usual on x axis. So we get this type of graph, this type of curve. Here you see solid line represents EMF, whereas dotted line represents current, alternating current. Okay, and the graph shows current lags behind the EMF by pi by 2. Okay, now for phasor diagram, we get this type of diagram. Okay, now straight line for EMF, and here you see this line represents current and this straight line represents EMF, and angle between EMF and current I is pi by 2, 90 degree. Okay, and this O to E, this straight line for EMF, it makes an angle of omega t with x-axis. Angle of omega t with x-axis. So from this combination, okay, inductor and alternating EMF, for that one we get two important informations. Number one, the peak value of AC is equal to I naught. I naught is equal to E naught xi L. Okay. And second point, very important point, xi L, we have considered xi L for omega L, xi L. Let xi L be the quantity omega L. That's why we know that omega is 2 pi upon T. Okay, omega is equal to 2 pi upon T, or we can write 2 pi F. Reciprocal of time period is frequency. So we can write for omega L 2 pi F L. Okay. Now since frequency for DC current is 0, therefore xi L will be 0. Xi L will be 0 for DC, direct current. But in case of AC, AC will have finite value. Okay, AC, because frequency is not 0 in case of AC. So AC will be, in case of AC, xi L will have finite value. So we get conclusion: an inductor offers an easy path to DC. Inductor offers an easy path to DC and a resistive path for AC.